Hello, 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 my Regents class. It really is probably going to be helpful if you use earbuds, but we'll see. Fortunately, hopefully you can hear me. And the only way that I'm going to hear you is through Kelly. So if you've got a question, please let Kelly know, and she will text me a question, tell me to stop, slow down, get shorter. Okay, I'm waiting for people to link on. I have 4 viewers. I know that everyone probably doesn't have a computer working, so 2 people can look at a computer, sure. Earbuds are definitely helpful. I think the sound will resonate and will have issues if you don't. But you can try without it, see what happens. I don't know. All right, so I'm going to first start for those. I'm going to first start with yesterday's worksheet. I want to get to the last one I left over. I know at some point you probably finished this or you have been looking at it, and I expect you to be struggling a little bit with polarity and polar bonds and maybe the Lewis dot diagrams of covalent compounds. So I'm going to spend today and next period you're going to be doing a lab. Hopefully that clears this up, and eventually my son will feel better and I'll be back in school. Okay. So what we're going to do is take out our worksheet, and I'm going to share with you my screen, and you're going to see the worksheet working together, kind of like we did yesterday. But yesterday was just me making a movie or a lecture, no give and take. Here I have an opportunity to stop and answer some questions. Okay, I guess you're going through Kelly to ask those questions. So let me share my screen, and we're off and running. Well, that's weird. Okay, so I'm going to go to, okay, so here I am back to where we were, and we left off yesterday with the idea that we have something called polar bonds and nonpolar bonds. Okay, and I want to make sure we're on the same page here. When we have 2 of the same nonmetals, they have the same electronegativity, so they share down the middle. If you watched my other 2 lectures that I posted yesterday, I do a very good job, probably a better job than I did yesterday in explaining that. So H to H and Br to Br are nonpolar. They don't have more electrons one side or the other, so there's no poles in their bonds. They're sharing equally. It's a nonpolar bond. And as we learned yesterday, hopefully, that to be a polar molecule, you have to have at least 1 polar bond. You have to have unequal sharing, because a polar molecule is a group of nonmetals where there is electrons, a lot of them in one side, but not a lot of them in the other. So it's an unequal distribution of electrons, and that creates differences, or poles that we like to say. Okay, so polar bonds are not the same element bonded to each other. So we identified that yesterday, like in the case of a C to an I bond. This is a polar bond. Here we're sharing electrons unequally. The more electronegative atom pulls them away. And then we brought that into the contents of the entire molecule being polar. And when we do that, we have to consider the 3-dimensional shape. And that's what I'm going to spend time on today. The idea, you have to be able to see this shape and be able to get it from the piece of paper. So let's start with water. Okay, the Lewis dot diagram for water suggests that oxygen has 6 valence electrons. We all should know it has 6. So if I go 1, 2, 3, and 4, I have 1 left. I have 2 left for 6, and I put them there. You certainly don't need colors, but hey, I like my colors. Then I have hydrogen. We also know that hydrogen has one valence electron. So I'm going to put that as the red. Boom, okay. Now, what we do is once you put out all the valence electrons and make at least one bond between them, and you may say, Mr. Grotsky, how do you know that oxygen was in the middle? I know that because oxygen needs 2 more electrons to make it bond, to make it have this stable octet. Remember, we put out the valence electrons and then we evaluate. This oxygen by sharing feels like it has 8. It was 2-6, but by sharing 2 electrons, it becomes 2-8, like a noble gas. It fills everything. And that's the driving force. Now, we're not transferring here. We're sharing, like ionic compounds transfer, because the difference in electronegativity is great. Here, it's similar. So we're forced to share. Now, hydrogen, we evaluate, has 2, just like helium. So everyone is structurally sound, or happy, or stable, okay? And again, if you try to do H bonded to H2O, it wouldn't work out. H bonds just once, and that's it. So you'll see that, mostly from experience. But hopefully that part is easy. Now the question is, the other questions that come are, number one, eventually is going to be, well, what kind of bonds exist here? Well, the bonds, again, there's 2 types of covalent bonds, really. There's polar and nonpolar. So the 2 bonds are between the H and the O. And we consider these bonds to be, yes, right, you're right, Tony. Okay, polar bonds. Why? Because they're sharing electrons unequally, even though I didn't draw them so unequally. And why? Because 2 different elements have what? 2 different electronegativities. So the one that's a higher electronegative, that attracts electrons more, pushes that pair closer to itself and makes this side of the bond be partial negative and this side partial positive. So we have 2 polar bonds here. Now, as we continue down this trek, we're going to ask ourselves, is the entire molecule polar? When you hear polar, am I talking bond or am I talking molecule? Okay. Now, the whole entire molecule, I've got to consider the entire shape. Does one side of the molecule have more electrons than another? I've been drawing this kind of ugly blob where you have more electrons on one side. That'll be the partial negative side, and the side that has less would be a partial positive side. And those are different, and therefore that's what polar molecules are. So we have to consider the shape. Now, the way that I drew this may make you think that water is linear. Okay, and why not? The way that I draw it looks like it's straight across. And this is where we're going to have to take this 2-dimensional shape and think about it 3-dimensionally. Okay, so I'm going to stop here and I'm going to go back to the video. I'm going to stop sharing and you're going to see me come back. And I'm going to talk about how electrons repel themselves into this shape. All right, now what we're going to start with, okay, and I don't have great models here, so we're going to use some toothpicks and grape tomatoes. How about that? All right, now this represents this grape tomato. All right, I guess I wish it was colored white. I didn't have any marshmallows, but okay, if you think about, okay, this grape tomato here represents an atom. Okay, that I just dropped. Okay, now what I'm going to do is I'm going to have it bond to another atom. Okay, so I'm going to kind of pierce it with a toothpick, and now I have, okay, a grape tomato bonding to another as it's dripping its tomato juice all over the place. Okay, now if you only have 2 atoms, they can only be linear. Now if something is linear, okay, the only way that it would be symmetrical, like in the case of, let's say, HI or II. Hold on, let me get a Sharpie. I'm thinking on the fly here. Okay. Let me get, maybe this will work. Okay, so if I have, H bonded to H, or HI. So here we go. Of course, it looks backwards, probably what you're seeing it. But the thing is, if I have these two, they're both linear, and they would look like this. Now, of course, H to H is symmetrical, and being symmetrical means that you're the same on both sides. Therefore, H to H is a nonpolar molecule. Now, it doesn't even have a polar bond, so that wouldn't work. But H to I, the second one, is different. Okay, as I lose, yeah, I'm getting tomato juice everywhere. This is not working out. But you notice the elements are different here. Okay, they're not the same, and they'll be asymmetrical. So the shape's important. So two things in a row represent something that we say is linear. Now, what if I had three atoms? Okay, don't know if I can draw this well. Three atoms, it depends. Okay, what I mean by that is it depends upon the central atom to see if it has electrons. See, electrons bend stuff different ways. And the way to explain this is go to an animation. So I'm going to share my screen again. Okay, and you'll see something crazy in a second. Okay, share. Whoa, that's crazy. And showing my screen, I'm going to pull this animation up. Okay. Now, what I have here is something that's going to show us something about this three-dimensionality. So let's go with two atoms. Two atoms, okay, are always linear. Now, what you're going to see with this is what happens when I change the electronegativity. Atom A and atom B right now have the same electronegativity. Right now, okay, it's a nonpolar bond, okay, and it's linear. Now, I'm going to put this electrical field on. No, let's keep that off. Electron potential, yeah. I'm going to make atom A have more electronegativity. And what you're seeing is an arrow getting bigger. What the heck does that happen here? Okay, now take the electric field off. And can I swing it back? Yeah, like that. Now what's happening, I go back. Here it's a nonpolar bond. The electronegativity difference is the same. So you don't see any arrow. Remember, yesterday the arrow represents a dipole moment. Now notice the colors are changing. These are called Spartan density maps. As A gets more electronegative, it pulls the electrons in this bond closer to A. And the red color means negative, and the blue gets positive. And the arrow gets bigger to show the difference in the charges growing. Smaller arrow, notice the colors get lighter. Until there's no colors, there's no arrow. Right now, nonpolar bonds don't have a dipole moment. But as I make A so much more different in electronegative to B, this gets really polar bond. Really red means a lot of the electrons are over here, and a lot of the electrons are missing over here. So we would say it's very partial positive. Okay, very important. Very polar. Okay, but now what if I did this? What if I made atom B become very electronegative, like atom A? What if the electronegativity difference starts getting similar? Then the bonds become almost nonpolar again. Okay, so that's important to see. Now, two atoms are easy. If you have one bond and you have a polar bond, the entire molecule must be polar. And which side is the negative side? The one with more electronegativity, which is attraction. Now, let's go to three atoms. This is where we're at with water. Now, if you think that three atoms are going to be linear, okay, remember we have oxygen in the middle. We're going to find out that that has a lot of electronegativity. And then we're going to say atom A has less and atom C has less. They're both hydrogens. Okay, now we don't have much of an arrow here because these things are straight across. The question is, right now this shape is symmetrical. These two polar bonds are the same. A and C represent our hydrogen. And the electronegativity difference is the same. You don't see an arrow, do you? But what would happen if I was to push A down and C down into a bent shape? You can see that there's an overall dipole moment up. Okay? And why? Because this is the positive side. So it gets polar if these shapes bend down. The question is, what makes them stay straight and what makes them bend down? Right now, this molecule is nonpolar because it's symmetrical. There's two polar bonds here because the electronegativity is different. But if I make them be asymmetrical, as we talked about yesterday, then this will be a polar molecule. When they are symmetrical, the same on both sides, they're not. That little arrow tells me that we have an overall dipole moment. Polar molecules have this arrow. So as the arrow gets smaller or disappears, it becomes what? More nonpolar. Now, question is, what makes them bend down? What makes them bend down, guys, is pairs of electrons either bonded or pairs of electrons on top. So the central atom, you have to count the electrons. So I'm going to go back to where I was, okay, and we're going to stop sharing this. And I'm going to go back to my fruit, hopefully it makes some sense. So back to my one grape tomato. And now what happens is oxygen in our drawing has two lone pairs and then it's a bond. And if you forget that, let's go back to that again. So I'm going to share the screen so remember. So back to water. Water has two bonds and two lone pairs, right? Here is one. Let's just color it in. Here are the bonds. Oops, bad Grodsky. Here are the bonds. Let's go down again. Christmas in July. So here are the bonds. I can do this. Why is that happening? I don't know. Not my day. Go back down. So I'm just going to circle them because I'm not sure what's going on here. But here are my two bonds. Too big. Here are my two bonds. And here are my two lone pairs. I have four pairs of electrons. Here's my oxygen. I have four pairs of electrons, whether they're bonded or not. And here's the important part of today. These pairs of electrons, whether in a bond or not, repel themselves into a very stable shape. And the drawing that you make two-dimensionally might not equate to how it exists three-dimensionally. Let me explain back to this. So what we're going to find, here's my fruit, okay? It's going to make four pairs of electrons. Now, here comes my sticks. What happens is, okay, it's going to make something called a tetrahedral shape. These electrons will repel themselves. I'm just going to put them together. I can make this happen. And I have two of the same, and then I have one coming at you. Trying to make a tetrahedral. So point down, I guess, a little more pointed down. And then one on top. Okay, so what I just made here from my tomato, I guess the tomato is a vegetable. I don't know, it's got seeds in it, so I guess it's a fruit. Okay, so here's my tomato. All right, what I just drew for you is a tetrahedral, or made, tetrahedral. These four pairs of electrons, okay, would repel themselves, I can do this, into this shape. And that's a tetrahedral. You say, what? Yeah, four pairs of electrons repel themselves into this shape. Now, if you notice, we have them are bonded. So I'm going to put two grape tomatoes on two of the ends. It doesn't matter what two ends I put them on. And what I get is I get this tetrahedral business, okay? I get this tetrahedral, but you notice there's two lone pairs. And these two lone pairs, if it doesn't fall, make something called a bent shape. So you may say, well, Mr. Grazi, how do I know it bends and doesn't go straight? Again, it's hard to think about these three-dimensionally, but this is a tetrahedral. You're going to see these in lab today. So 4 pairs of electrons make a tetrahedral, but where the atoms are is where we figure out the geometry. So this is a bent shape, okay? And I'll make it again. Maybe I'll use grapes. No, we'll do tomatoes again. So it's a firm grape tomato. So here we go. I have my 1 grape and 3 pairs of electrons, 4 pairs of electrons on the central atom will cause it to bend downward, and 1 on top. Okay, so I got these 3, and I got 1 on top. Make the yellow on top. Believe it or not, that's a symmetrical tetrahedral, although, again, not the greatest at doing this, okay? And then if I was to put tomatoes, okay, where the H's would be, you'd get that. So here's 1, and here's 2. And what you wind up having is you wind up having a tetrahedral shape, but only where the tomatoes are, you consider the shape. Although mine's kind of bending here. That's a bent shape. Now what's bending it downward? These 2 lone pairs of electrons on top are bending it downward. If these 2 lone pairs of electrons, and this is the key to the entire thing, if these 2 lone pairs were not here, if I was to take these 2 lone pairs right here out, they wouldn't bend it down the shape, and this water would be linear. And if it was linear with an O in the middle and 2 H's, it would be very symmetrical. And water would be nonpolar. But because we do have 2 lone pairs of electrons right there, I'm just getting tomato all over my computer. Not what Apple had in mind. I guess they wanted apples on their computer. I'm not sure. So at these 2 lone pairs, bend these what? Bend these other electrons in the bond downward because electrons repel themselves. So the lone pairs. Now you may say, Mr. Grazi, why do you draw it that way? How come on the worksheet you drew it that way? Well, if you think about it this way, and again, you have to think 3-dimensionally. If you look at it straight, in fact, I drew it this way, right? I drew it flat. If you look at it this way, and again, I'll take away this, the left and right are straight, and you think it's up and down. This is a 3-dimensional drawing, but if you look at it this way, you think, wow, it's linear. No, no, no. Don't confuse yourself. I drew it this way. The top and bottom toothpick look like they're flat. Looks like it's a cross. It's not. It really is this shape. So you've got to think 3-dimensional. Oops. So back to where we were. Let's go to the screen. Let's go back to the journal here. And back here. So I drew this. Let's go back a little bit. I drew all these things. Look at water, how I drew it. Oops. All right. I drew it flat. It looks like it's linear. But what do you know? The central atom has 2 lone pairs who are doing what? Who are pushing down the other bonds to make it look like, or to make it into what we call a bent shape. And the H's come by, and they give an electron, we'll make it red, and this is a better way to draw it. This kind of tells you, oh, the 2 lone pairs bends it down. So you need to know this is called a bent shape. Now you could draw it this way, but you might fool yourself to thinking this molecule is a polar molecule. Let's go over. Definitely has polar bonds. Check. Polar bonds. 2 different nonmetals will share electrons unequally. So this has polar bonds. It's the first requirement to be a polar molecule. Number 2, it is asymmetrical now. Because these lone pairs push it down, it is asymmetrical. And if it's asymmetrical, that means the polar bonds don't cancel themselves out. And you're going to have an overall positive area, and an overall negative area. We always draw the arrow toward the negative area. So again, hard to draw these two-dimensionally. You have to think three-dimensionally. Let's stop sharing. Let's go back to my terrible water molecule. Okay, here it is. Here it was. And these poor tomatoes are getting pierced. Okay, they're not into piercings, but I'm really giving it to them. All right, so I have my two impaled, and they're getting kind of loose here. But here's the shape. It's bent. Why is it bent? The lone pairs are pushing it down. All right, and because of that, what we have, party people, is we have a positive area. Remember, the electrons are being pushed up toward the oxygen. So these electrons here go upward to the oxygen. Therefore, these H's, this side is the positive part of the water molecule, and this side where my hands are kind of holding is the oxygen. So the oxygen is right where my thumb and finger are. That's the negative part. Positive part, negative part, unequal distribution, polar molecule, but that's because of the asymmetry. Okay, now getting back to where we are. Any questions? I don't see any. I'm going to continue because it's important to think about three dimensions. Let's go back to our worksheet. And let's go back to our worksheet. Let's go to the top. So water is a polar molecule. And by the way, the famous boyfriend, famous girlfriend attractions we learned about only occur because water is polar. Now let's go to CO2. All right. Now you should have drawn CO2 already. Okay, so I'm just going to quickly put this out here. Carbon in the middle. Here's my oxygens. I don't know if it's linear, but I'm starting this way. Carbon has 4 valence electrons. So I go 1, 2, 3, 4. Oxygen has 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and 6. Okay, party people. I am now going to make one bond. All you do is make a bond. So I have one blue. Oops, I don't want that. I want this one. I bring this in, and I bring another bond here. And what do? I evaluate. I see how many electrons this guy has. This oxygen has 1, 2, 3, 4, 5, 6, 7. This oxygen has 1, 2, 3, 4, 5, 6, 7. No good. Oxygen wants to have that 8, that octet rule. How about the carbon by sharing? The carbon by sharing has 1, 2, 3, 4, 5, 6. Nobody is stable. Nobody is happy. This is not correct yet. What do? Kara, pay attention. What do? You add another bond. That's right. So I put another pair together, and I pull that together. And now if you evaluate and see how many they're sharing, you can see that this oxygen feels like it has 8 by sharing another pair. This one feels like it has 7 still, so what we're going to do is we're going to make another bond. Put this pair here, put this pair here, and then we're going to share. And we evaluate. This has 8. Each oxygen has 8. And this is amazing. This carbon now has 8. They're as stable as a noble gas. So what we had to do to make this work, party people, is we had to make a double bond. Now I can rewrite this. I can write carbon as a double bond to the O, put the lone pairs, another double bond to the O. Now, this is where I'm talking about, party people. Does carbon have any unbonded electrons above and below the carbon? Remember, these two bonds are directly on the other side of each other. Is there any lone pairs that are on the carbon? Of course not. I used all of the carbon's electrons as bonds. So there is no bonds that is going to do what? Bend this downward. So my friends, in chemistry, CO2 stays linear. And because it stays linear, we know that the molecule must be what? Well, I'm going too fast, the first thing we ask ourselves, do we have a polar bond? And the answer is yes. The bond is polar because there's two different elements sharing unequally. Oxygen is more electronegative than carbon, so these guys are pulled closer. So there is 4 polar bonds here. So this thing could be a polar molecule. The second thing, is it asymmetrical? Is it asymmetrical? Well, we know because there's no electrons above and below to bend this, so this thing is very symmetrical. Being symmetrical, can you turn it down, Red? Being very symmetrical means that, like I showed you with that animation, means that this cannot be a polar molecule. These polar bonds or these dipole moments cancel. So because it's not asymmetrical, this can't be a polar molecule. These polar bonds cancel out, and this is a non-polar molecule. If you had, let's pretend I'm a princess and we had a lone pair up here. If there was a lone pair, it would bend it downward. If it bent it downward, you would have what? An asymmetry and a negative and a positive part. But because there is no lone pairs, and we only know this by doing the Lewis dot diagrams like we did, because there is no lone pairs, it stays linear. And because it's linear, it's symmetrical. Because it's symmetrical, the distribution of electron charge is even. And if it's an even on both sides, there's no poles. To be a polar molecule, my friends in chemistry, or not to be. That's the Shakespeare question. To be polar, you must have polar bonds. This does have polar bonds. And you have to be asymmetrical. Darn it, that didn't work. This is symmetrical. Look at water. Water is polar because it has polar bonds. There they are, 2 different nonmetals. And because it's bent downward, because those lone pairs push down those grape tomatoes, okay, it is not the same all the way around. All right, the dipole moments do not cancel, and you're going to have an overall positive area and a negative area. That's the key to knowing about 3 atoms. All right, let's try the next one, number 11. All right, number 11. Number 11 is called ammonia. Let's make some room for it. Let's give a hand for number 11. Hey, okay. Now, let's do the Lewis dot diagram. Here's my N. It has 5 valence electrons, so I put out 5 dots. Each H has 1 valence electron and 1 dot. And you can see that's a very, very stable structure because by sharing, the what? The nitrogen is stable by sharing 3 more. And each hydrogen is stable because they feel 2 by sharing. They're using each other to get stable. Okay? So the question is this a polar molecule? Well, we go through our checklist. Do we have polar bonds? Do we have polar bonds? And the answer is yes, we have 3 polar bonds. Do we, remember, saying polar bonds means you have what? 2 different nonmetals. So we have 3 polar bonds. So that part of the checklist has been satisfied. Second thing, is it asymmetrical? Well, is it the same all around? To be symmetrical, you have to be the same all the way around. Is this the same all the way around? And you would say, no, it is asymmetrical. Therefore, this is a polar molecule. Now, why? Well, it looks like it's flat, but it's not. There's another way to draw this, and I'm going to do this for you, see if you can understand. Sometimes I'll draw this 3-dimensionally in a higher level course. So make this a little bigger, see if you can get this. And I know the bell's going to ring on me, so I'm going to pause here. Okay, and we're going to come back in about 4 minutes, and I'm going to do a little 5 or 10 minutes more, and then I'm going to set you up for the lab, which is going to put all of this together. Okay, so take your break.
Daddy's on fire. Fire.
Is that right?
He's on fire.
Who's on fire?
The car will burn. Because he did burn. That's why it burned. Nobody smokes it. That's one thing he had. But he didn't burn again. Lots of money. It made a lot of money. I won, Daddy. Won. Score. Pretty score. Pretty score. Pretty score. I got free. So I just ran out of juice.
What's that?
I did this one out of juice.
Oh.
Because it was nothing on it.
Here, Raven.
What's not going on?
Mom's coming home at about 3 o'clock.
Later?
Yeah.
In the afternoon?
Well, it's almost 1 now, so it's a couple hours.
It's the afternoon now.
Yep. Okay.
Yeah, where did you get these sticks from?
No, in the cabinet. Okay. All right, so we're all back. All right, I don't want it too much longer. I know I'm killing you with, and again, when I get into class tomorrow, hopefully my son's better. You feeling better, Brady? Okay. Hopefully tomorrow is it. I'm going to show you from balloons why they make the shapes they do. But so far we have a couple of shapes. We have linear, we have bent, and I'm going to introduce tetrahedral to you and this shape right here. So what is this shape right here? Okay, clearly this is going to be a polar molecule. Now, why is it a polar molecule? Because it has 3 polar bonds, and it's not the same all the way around. So it's asymmetrical. So to be polar or not to be is the question, okay? So it has polar bonds, 2 different nonmetals, and it is asymmetrical. Looks like I spelled something bad there. Asymmetrical, okay? Have to continue the string there. Nobody mentioned that, of course. All right, any case, what is this shape? Now, it seems really weird, but the shape is actually going to be trigonal pyramidal. I mean, so what the heck does that mean? It means you have a triangle of a pyramid, or a 3-sided pyramid. Now, let me help you draw this 3-dimensionally. I'm going to get rid of some stuff here so I can draw. So here's how it would look. What you have is you have the N in the middle, and you have it bonding to an H, and it bonds to another H that kind of comes at you. So this dark line means it's coming at you. And then there's a dotted line. Dotted line means it's coming behind it, and there's an H. So this dotted line means it's coming behind. And then we have a lone pair up here. So if you can think with me, what you have is this lone pair, okay, which pushes downward these other bonds, these other electrodes downward into a top of a 3-sided pyramid. Now, when we consider the shapes of the molecules, we just consider where the atoms are. So here, 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 and here. That if you can understand that, that's coming at you, this is going behind you. What you have is a 3-sided pyramid. Okay, hard to draw. Okay, and what keeps these dashes down is the electrons bend them down. So it's trigonal planar is the same thing as saying triangle pyramid. So let me try to show you that with some fruit. I know that I'm probably not being very successful, but I am being very tall. Okay, so let's try this again. All right, I think I'm going to give up on the tomatoes, and I went to some grapes here. All right, so what I have here is, here we go. Again, this will be the N in the middle, and hard to do this. I'm kind of guessing here. They're going to bend downward. And you could see it's the top of a 3-sided pyramid. Okay? And the thing is, the reason why it's the top of a 3-sided pyramid is because this lone pair, which is the blue toothpick, bends it downward. If it wasn't there, these would all flat out on the same plane and be trigonal planar, not one you need to know. But this lone pair, in fact, I forgot. I have to add the what? The hydrogens. So there's that, and there's one more grape. And the grapes are working better if you needed to know. So there is my shape. The end in the middle, 3 grapes pointing down, and what's pointing down? And each of these sticks represent a pair of electrons. The top pair, the blue one, is pushing the other 3 downward, okay? Oops. And we say we have a top of a 3-sided pyramid. And this is a stem that's just there. Don't confuse yourself. All right? So this is a, guess what? A trigonal pyramidal, or trigonal pyramidal, or just triangle pyramid. That works as well. Okay, so no biggie. Let's go on to the last shape you have to know, and that's, I think, the easiest. Okay, and let's do it. Let's go cancel. Let's yes, Brayman. Yep, it's a battery. Okay. Okay, you go crazy. Okay, so the next one. And again, that lone pair pushes it downward. Now, let's go to let's go to one we already did before. Let's go back to this shape, CH4. And let's get some stuff out of the way here. CH4 we already did. Okay, let's get these circles out of the way if I can. I'm almost, oh, Christmas in July, what happened? Oh, okay. I don't know what's happening here. Get rid of these. Okay, so we can see. Okay, so this is methane. Now, we draw methane like this, a C, a bond to the H. Notice that a pair of electrons is a bond. Boom, we draw that. That looks like it's very symmetrical. Okay? And you're right, it is symmetrical, but that's not really the shape. 4 pairs of electrons go in a tetrahedral shape. Okay, and that's what I was trying to show you before. All right, and how would that look? Carbon in the middle. We have one coming up, one coming down. This is the H. Now I'm going to have one coming at you. That's the thick one. And one kind of going behind. That's the dotted one. And you can see that shape. By the way, can you see? Can't you see? Can't you see that this is the top of the pyramid thing we just saw? But putting an H here, we have something called a tetrahedral shape. All right. Christmas in July. I just went blank. Here I am. So this has 4 polar bonds, but this shape is symmetrical. Don't fall in love with the fact that it's flat. When you do the models today, you're going to see that carbon has holes in it in these directions. You're going to see that. If I stop sharing, okay, back to my ammonia. Here's my ammonia, but if I put my what? My last grape up top, now I've got my tetrahedral shape back. Okay, something like that. My fruit is not being good to me today. Okay. All right. So there's my tetrahedral shape, sort of. Okay. And believe it or not, it is very symmetrical. Okay. And because of that, the 4 polar bonds cancel out. Except though, if one of my if my finger becomes another element. So if this becomes, let's say, I don't know, a bigger tomato. Now it's not symmetrical. That tomato makes a difference, and now it's asymmetrical in the case of CH3I. So we have 4 shapes. Let's go back and let's put them on a piece of paper so we understand. The 4 shapes that we have are the following. We have tetrahedral. That's with it. So tetra means 4 sides. So anytime you have 4 things coming around and are bonded, it's a tetrahedral. Okay, and that's what this is. Then we had the top of a 3-sided pyramid. Okay, and that's what this is. Trigonal pyramidal or triangle pyramid, good for me, is that right there. Then if you just have 2 things, but if they're in straight line, we have linear. Now I know that this is linear because carbon doesn't have a central atom to bend it down. So we've got linear. We have top of a 3-sided pyramid, trigonal planar. I'm sorry, trigonal pyramidal or triangle pyramid. We have the tetrahedral that we just drew here, somewhere right here. And then the last one is when it bends down, like in water, it's bent. So those are your 4 shapes. Now, let me draw water one more time and I'm done. How can I draw water one more time to make sense of it? Here we go, party people. Here's my oxygen. And there's 4 pairs of electrons that surround the central. So here's an H, Okay. Let's draw the H coming at you. Then I have one that's going away, and that is a lone pair, and this is a lone pair. So the two lone pairs bend this down into a what? A bent shape. Okay, so those are your shapes. So in today's lab, and this is what you're going to do. You're going to take your lab, which I have posted. I don't have hard copies because I'm not there to print them out for you. But you're going to see a lab. Okay, if I share my page, stop sharing. Okay, and then share my, share screen. Let's go to the web page. Sharing my screen. Okay, share. Okay, let's go to the web page. All right, let's go to our class web page. Okay, and you should see right here, Lab 12 Regents Model Kit. What I want you to do is I want you to download that and then print it. And when you have that, what you're going to do is you're going to grab a gray kit, a molecular model kit. And in that molecular model kit, you're going to build the atoms. You're going to write the Lewis dot diagrams, and then you're going to put the molecule together based on the color codes on the front part of my lab, and I want you to build the atom. Follow these rules. Why? The reason I want you to build the atoms is the same way I was playing with fruit today, okay, and impaling the fruit today. I want you to see the three-dimensionality. If you build a structure that's symmetrical the same way all the way around for all the atoms, it's going to be a nonpolar molecule. If it's asymmetrical, okay, you should be able to determine that by it not being the same all the way around. So you should be able to predict it with Lewis dot diagrams, but confirm it with a three-dimensional structure that the kits will allow you to do. So download this, print it out, put it together, start writing your Lewis dot diagram, predict. Okay, now I want to show you, so hold on to your ponies for a second. One more thing. Let's just make this out here. Okay, so on the first page of your lab, okay, I'll give you the objectives another day. I have all the rules, and these are color coded for your kit, so you're going to build them. But this is what you're going to do. Starting in order, you're going to write the Lewis dot diagram. The ball and stick model is, if you think it's linear, you would write it like this. Okay, here's my ball and stick. What kind of bonds exist between the atoms? And the type of molecule, is it a polar molecule or a nonpolar molecule? And then you're going to tell me the shape. Now your shapes, of course, are going to be linear, tetrahedral, bent, or that three-sided pyramid called a triangle pyramid. Okay, so Lewis dot diagrams. I'll do that for you. This is going to be a nonpolar bond, right? Because it's the what? Same atoms bonded to the same atoms. This molecule is clearly going to be, okay, going to be nonpolar. And the shape, of course, is linear. And you're going to do that for all of them. Why do you need the models? You need the models to help you create the three-dimensional structures. Okay? Good luck. I'll be standing around if you have questions. Ready, set, go.